Hello, welcome to the part 2 of Math 21 Final Exam Review. I call this section Other Functions and Properties, and you hit pause if you need a listing of the problems that this covers. Again, some of these are very similar, so I don't necessarily do every single problem, but I do every single skill, and I'll give you the second or third problem to do your practice. All right, there we go. So first, let's find the difference quotient. This is a little bit of algebra of functions. Here we're going to subtract some functions. We're going to divide some stuff. The difference quotient is a huge concept. So I'm going to do a couple of these. I don't do all three of them. But we'll do one as a basic example, and then we'll do another one that's a little more challenging. That is the type of thing that you really need to become comfortable with if you're moving on to calculus. So find the difference quotient, where h is not 0, of f, and simplify. Our function is given by f of x equals 7 minus 12x. Every single time we have 3 steps. First step, find f of x plus h. So everywhere we see an x, right, 7 minus 12x, we're going to replace that x with parentheses and call it an x plus h. I put x plus h in there because we're not evaluating x anymore. It's not 12 times x. It's now 12 times x plus h. So 7 minus 12 times x plus h, we could distribute that negative 12, and it becomes 7 minus 12x minus 12h. Second step, complete the subtraction in the numerator of the difference quotient. Find f of x plus h minus f of x. Now, don't reinvent the wheel here. You have f of x plus h, so I just type that out again, and then subtract, and since it's subtraction, I put the original function in parentheses to make sure I distribute my negative. Always want to distribute my negative. Let's use the pen here. That minus 7 and the positive 12x will cancel from f of x plus h, and the only thing left is our negative 12h. And you'll find this happens quite frequently. All right, that right there is an important check. Does everything remaining have an h in it? If it does not, you did something wrong in step 1 or 2. If it does, you're probably okay. Step 3 is then to divide by h, and again, I'm not going to redo all the work. I'm going to take my result from the previous step, negative 12h, divide it by h, and get negative 12. Now here is the biggest mystery around the difference quotient. I'm going to tell you calculus before you're even there. All the difference quotient represents is a slope. This is just a fancy calculus way of saying, hey, find the slope. What's the slope of 7 minus 12x? This is a linear function with slope negative 12. The difference quotient gave us negative 12. So when you get into calculus next semester, or whenever you happen to take it, all a difference quotient is a slope. Calculus demystified. All right, so let's try it with a more challenging function. X squared minus 2x is our f of x. Same 3 steps. First, we find f of x plus h. Now, everywhere there's an x, we replace it by x plus h. So instead of x squared, we have x plus h squared. Minus 2x in the original becomes minus 2x plus h. Don't forget to actually square out your x plus h. You want to square it, and let's use blue. I'm tired of red. This x plus h squared is x plus h. Mouse for writing, pretty awesome. Times x plus h. So we'll have x times x to give us x squared. X times h and another x times h to give us 2xh. And h times h to give us h squared. So I'm going to put a little umbrella there. Don't forget to multiply it out. That's the biggest mistake people make. This is not just x squared plus h squared. You have to have those middle terms as well. Distributing the negative 2 to the x and the h, fairly straightforward. Minus 2x minus 2h. So we have f of x plus h right here. That's a big, long expression, but that's all right. We're going to use it here. in step 2, f of x plus h minus f of x. So I don't reinvent the wheel. I put down what I had in my last step, subtraction. Subtract the original function, so I use parentheses around the original function, the x squared minus 2x. Notice I'll have an x squared. Here I have minus x squared, so they cancel out. Here I'll have a minus 2x, minus a minus, so positive 2x, so the 2x's cancel out. I'll have the 2xh, I'll have the h squared, I'll have the minus 2h. Everything that remains after step 2 has an h in it. So I know I probably did it right. There's a good chance that it's correct. So when we write 2xh plus h squared minus 2h all over h, it's easy just to start canceling your h's all just randomly. I encourage you to take that extra step where you factor an h out of everything from the numerator. Then you can see exactly what you're doing as you're canceling these. The h's cancel. We'll get 2x plus h minus 2 as our difference quotient. Now, this doesn't look like a slope, right? But this is not a linear equation. So calculus will deal with how this can become a slope of something that's not a straight line, right? But that's beyond the scope of this particular review. All right, let's write the new function f of x that satisfies the following conditions. So it's got to be the absolute value function. It's going to be reflected with respect to the x-axis, compressed by a factor of 1/3, shifted to the left 3 units, and up 5 units. So is reflected with respect to the x-axis. So if the x-axis is our mirror, we're looking at a vertical reflection. All right, so a vertical reflection is going to be on the outside. All right, so that's where we get our negative. Compressed by a factor of 1/3. It doesn't say horizontal or vertical, so if it doesn't make a distinction, we're going to assume vertical. So vertical compression of 1/3. Shifted left 3 units. Left 3 units. Anytime we're going horizontally, left or right, we're inside with the x. Horizontal compression, horizontal stretch, horizontal shift left or right. It'll be inside the absolute value or inside whatever the function is. And left is going to go plus 3 because it goes to left. X minus our h value, x minus a negative 3 becomes x plus 3. And finally, running out of colors, I guess we'll go with another blue, our plus 5 when we go up 5 units. I forgot to underline left 3 units in purple, but you get the idea. Let's do another one of these, though, because it's kind of tricky sometimes. This time, we have y equals x to the 5th, stretched by a factor of 3, shifted to the right 3 units and down 3 units. Now, first of all, I should have written f of x here, because I want a new function f of x. So that's wrong every single time. My bad. I just noticed it. All right, so stretched by a factor of 3, I'm going to multiply by 3, stretch it out. It's like we're grabbing the ends and just pulling them apart so the curves are a little thinner, more narrow. We have, let's go with green, shifted to the right 3 units, shifted to the right 3 units. And let's go with an annoying red, down 5, up and down, vertical translations, those are on the outside. So the minus 5 is on the outside. We'll throw a little f of x on here instead of the y, and we have completed the problem. All right, good job. So we want to make a table of values and then graph a piecewise defined function. And here I use Desmos.com. I love Desmos. It has great graphing utilities. And there are some very creative people that can draw some amazing things on Desmos. All right, so a piecewise defined function. Mathematicians are highly intelligent, of course, but not super clever. We call it a piecewise defined function because it's a function defined in pieces. It's easier to keep track of it that way. So I'm going to call this the top piece. The top piece only because it's listed in the top of the parentheses. X minus 2 for x less than or equal to 1. So looking only at the top piece, y equals x minus 2. My x values have to be less than or equal to 1. So I want to start at 1 and go less. And by less, right, to the left of, it's actually pointing the direction we should go. With this equal sign, that tells me that I'm going to have a solid dot when I plot here at 1. So that looks like a negative. It's not. That's a solid dot. There we go. Make it a dot. A solid dot. So we'll have 1, negative 1, solid dot. We'll have 0, negative 2. We'll have negative 1, negative 3. And we know this is a linear function. We know we could draw the line, and there we go. Now let's look at the top piece, the bottom piece. Notice this graph, this we'll call it red, this red graph is only for x values less than or equal to 1. I don't go past 1 at all with this piece of the graph. It's literally just a piece of it. So then when I graph y equals the square root of 3x plus 1 for the x values greater than 1, which I should have put here, you'll only find your mistakes no matter how many times you review it after you're talking about it. So again, I start at 1, but since it's not an or equal to, I want to make sure I use an open circle here at 1. When I put 1 in for x, 3 times 1 is 1. That's not true. 3 times 1 is 3. 3 plus 1 is 4. The square root of 4 is 2. So I have the point 1 comma 2. I use an open circle. It says if we could use the value 1, this is what it would be. We can't use the value of 1, so we'll use an open circle to indicate where it should have been. Now if I put 2 in here, 2 times 3 is 6, 6 plus 1 is 7. I have no idea where the square root of 7 is on here. I'm going to guess it's about right there. But I get to pick the x values. I'm going to pick x values that work. 3 times 3 is 9, 9 plus 1, 10. I don't know the square root of 10 off the top of my head. 3, 4, 12 and 1 is 13, 5, 15 and 1 is 16. Hey, look at that. The square root of 16 is 4. I have another exact value that I can plot. Put in 6, I have 18 plus 1 is 19. Put in 7, 21 plus 1 is 22. Put in 8, 24 plus 1 is 25. Oh, look, the square root of 25 is 5. I have another value exactly. When you get to pick the x values, how about you pick some values that work out for you so you don't have to do decimal approximations? Again, we only graph this starting at 1 and going bigger because it tells us x value is bigger than 1. And we have the other piece of our graph. Piecewise defined functions. Take them a piece at a time and never cross that magic cut point line and you should be good. All right, let's talk about composition. Composition of functions is the fifth operation on functions. Addition, subtraction, multiplication, division. Composition is the fifth operation. And really all it is saying is we're going to evaluate one function, f, using a different function, g of x. So instead of f of x, it's f evaluated at the function g. All right. So as I'm doing compositions, I always work from the inside out. The inside, g of x, I'm going to replace that. F parentheses, I know what g of x is. G of x is given by x plus 4 over 3. So I put x plus 4 over 3 where there used to be a g of x. Now I'm looking at just f evaluated somewhere. What is f? This function f is 3 times something minus 4. So when I start this, I literally put 3 times something, my parentheses aren't curving right, minus 4, and then I put the g of x in that open parenthesis space. This is called a skeletal model. What is f? F is 3 times something minus 4. Instead of calling it x, instead of calling it something, let's leave a set of open parentheses. 3 times something minus 4. And then we can put exactly what that something, 3x plus 4 over 3, is. All right, so now that we've evaluated a function at another function, let's simplify. 3 and divided by 3 will cancel out. I'm left with x plus 4 minus 4. There's no longer a reason for the parentheses. X plus 4 minus 4 gives me x. Similarly, when I'm doing g of f of x, I'll put f of x. I don't want to call it f of x anymore. That's like when your mom calls you your formal name, but your friends call you whatever your friends call you. That's probably not appropriate for your mom to hear. G of f of x equals g of 3x minus 4. Well, what's g? G is something plus 4 all over 3. So instead of calling it something, instead of calling it x, those parentheses, I put in exactly what I'm supposed to. I'm supposed to put in the 3x minus 4 in place of x inside the parentheses. 3x minus 4 plus 4 over 3. Simplify the numerator first. The minus 4 plus 4 cancels out. We'll end up with 3x over 3. And the 3's cancel to leave us with the x. Now, this is unique. You know how you could add 3 plus 4 and get 7, and you could switch those around. 4 plus 3 is still 7. 3 times 4 is 12. 4 times 3 is 12. It doesn't matter the order you add or multiply. Those are called commutative. However, if we have subtraction, right? 5 minus 2 is 3, positive $3. But if you have 2 minus 5, it's a negative 3. So subtraction matters, right? 3/4, 4/3. Division matters. In general, composition order matters. Composition is not g composed with f of x is not always the same as f composed with g of x. However, when the composition in both orders results in the identity, so what you put in, x, is what you get out, x, then these two functions are inverses. All right? That's the definition of how we know when two functions are inverses. If the composition in either order results in the identity, then these functions are inverses, and that's exactly what we have here. All right, speaking of inverses, how do we find inverses? Well, there are a couple of different ways. In this particular example, w of x equals 2x to the third minus 5. We don't know what w stands for. We don't know what x stands for. We're going to assume that it's just some random name, just w, because people are tired of writing f. So when we do an inverse where there's no word problem to back it up, w of x equals 2x cubed minus 5. Our first step, rewrite so it does not have function notation. I'm going to call it w equals 2x cubed minus 5. Because the w and x do not represent anything in particular, our inverse property, the inverse, all it does is switch the value of the switches the variables. So that's exactly what we do. What was a w becomes an x. What was an x becomes a w. And now we solve for w. So in order to solve for w, let's add 5 to both sides. We'll get x plus 5 equals 2w cubed. Next step, we're going to divide both sides by 2. We'll get x plus 5 over 2 is w cubed. And we still want to get w by itself. The opposite of to the third power is the cube root. Right? Opposite of cube is cube root. And it's the cube root of the entire left side. So cube root of x plus 5 over 2 equals w. But remember, it was given to us in function form. If we're given a function form statement of the question, we should give a function form answer for the question. So w inverse, w to the negative 1 of x, is equal to the cube root of x plus 5 over 2. Again, if the w and the x stood for specific things, we wouldn't have switched the values of the variables. But when it's just a function, absolutely, second step, switch x and w and go from there. All right, let's find the inverse of f of x equals fifth root of x plus 7. So the fifth root of x plus 7, again, we just have a regular old function. So I'm going to rewrite it in the variable y. Y equals the fifth root of x plus 7. All an inverse does is switch x and y. So what was a y becomes an x. What was an x becomes a y. Now we want to solve for y. So the opposite of the fifth root is the fifth power. So we'll take the fifth power on both sides. X to the fifth equals y plus 7. We'll subtract 7 to get y by itself. And that seemed a little too easy, but it's okay. Math can be easy. Remember, we're given function notation to start, so we make sure we finish it with function notation in the end. We want to find the inverse of each function. It tells you exactly how to write your answer. F inverse, f to the negative 1 of x equals x to the 5th minus 7. All right, let's talk about polynomials. State the degree and leading coefficient of f of x, which is equal to 3x cubed plus 18x squared minus 12x minus 72. The degree is the highest power of any of the variables, so the degree is 3. And the leading term, the leading coefficient, that's the 3 we're referring to for the leading coefficient. The fact that they're both 3, a little bit of a bummer, but that's the way it goes. All right, so find all x, part B, find all x such that f of x equals 0. Solve algebraically and show your work. Literally, f of x is the same as 0, so where I have an f of x, I'm going to replace it with a 0. If 0 equals 3x cubed plus 18x squared minus 12x minus 72, I noticed that the 72, 12, 18, 3, they're all multiples of 3. So why use big numbers when we could use smaller numbers? Let's divide everything by 3. 0 divided by 3 is 0. 3x cubed divided by 3, 18x squared divided by 3, minus 12x divided by 3, and minus 72 divided by 3. Fantastic. This polynomial, x cubed plus 6x squared minus 4x minus 24, has smaller values. It's a little easier to work with. We had something called the rational zeros theorem, and the rational zeros theorem tells us that the rational zeros of this polynomial will consist of all the ratios of the factors of the constant term divided by the factors of the leading coefficient. Now, the leading coefficient is 3, but we're working with the 1 after we divided, so we're using the 1. So all the factors of 24 include 1, 2, 3, 4, 6, 8, 12, and 24. All the factors of 1 are 1. I like ones. And remember, they could be positive or negative. So all the different possible rational zeros are actually integers, and I like it when they're integers. But you see, the thing is, these are not all actual rational zeros. This just tells us where to start. We have to do some work. So we do that work on scratch paper. So x cubed plus 6x squared minus 4x minus 24. I have the list of my possible rational zeros, and I start at the beginning. I'm going to try x equals 1 with synthetic division. So we'll put 1 in the box. The coefficients 1, 6, negative 4, negative 24 along the top. And the pattern is we drop the leading coefficient and then multiply to go up and over. So 1 times 1 is 1. Add straight down. 6 and 1 is 7. 7 times 1 is 7. 7 and negative 4 makes 3. 3 times 1 is 3. When we add straight down, if we don't get a 0, we don't want it. And this is the remainder theorem. It says if a polynomial is divided by k and the remainder is 0, then f of k is a 0 of the function. All right, f of k is a 0. So no 0 on the remainder, not a factor. So let's try x equals negative 1. Bring down the 1. Negative 1 times 1 is negative 1. We'll add straight down and get 5. 5 times negative 1 is negative 5. We'll add straight down to get negative 9. Negative 9 times negative 1 is positive 9. Add straight down is not 0. It doesn't matter what it is. It's not 0. Tried 1, tried negative 1, so now I'm going to try 2. When I try 2 with my coefficients 1, 6, negative 4, and negative 24, I drop the 1. 2 times 1 is 2. Add straight down to get 8. 8 times 2 is 16. Add straight down to get 12. 12 times 2 is 24. Add straight down, we get a 0 remainder. That's awesome. We know that x equals 2 is a 0, which tells us the x minus 2 is a factor. And we have our quotient right here. we've divided. This is synthetic division. So our quotient says, since this is x cubed, let's see if I can get a 3 up there. I know that this one must be x squared, always 1 degree less in synthetic division. X squared plus 8x plus 12, and I can factor that. And once I get it down to a quadratic, I don't have to use this method anymore. Why would I keep doing the hard work when we could factor instead? So x squared plus 8x plus 12 can be rewritten as x plus 6 times x plus 2. So we know that x equals 2 is a 0, and we have the factored version of the quotient. So we can see that our zeros are -6, -2, and the +2 that we used in synthetic division. You could keep going. You could have tried -2 next, and 3, and -3, and 4, and -4, and 6, and -6, and finally arrived at your answers. But sometimes use these big hammers when you need to, but sometimes an itty-bitty little tack hammer is all you need in order to finish the problem. All right, so I'm not entirely sure why this is in a box, but that's all right. Let's describe the end behavior of this particular graph. We know it's a cubic equation, so the ends will finish in opposite directions because every odd graph does. We know the leading coefficient is positive, so it will generally be increasing. So our graph is going to be something like this. So we know that f of x goes to -infinity when x goes to -infinity. And we know f of x goes to positive infinity when x goes to positive infinity. So this is how we would write our end behavior. Sketch the graph on your calculator so that the key elements are visible, and then sketch it by hand. I'm not going to sketch it by hand, but I did show you here on my calculator and my window settings. As I type in the original function, we can see our zeros at 2, -2, -6. I made the window appropriately sized. I'm not going to use an extended -10 to 10 window for x because I don't need all of those values. I'll go a couple above the highest 0 and a couple below the lowest 0, and it's all good. And my y values, I did have to extend a bit in order to see the maximums and minimums. How many turning points does the graph of f of x have? Now we could go back to the previous slide and see that there were 2 turning points. There was a maximum and there was a minimum. But in general, the number of turning points is 1 less than a degree. How many inflection points? How many inflection points does the graph have? I'm going to go back. An inflection point will occur right in this area. We can see that this part of it is cupped down, but this part of the graph is cupped up. This hinge point is exactly where you're going to find an inflection point. And it's always 2 less than the degree. So the degree is 3. There are 2 turning points. There is 1 inflection point. At what point does the local maximum occur? Let's round our coordinates to 1 decimal place. And let's pull up our calculator and check out how to find the local maximum. So in my y equals, I'm going to put in my function. Make sure you come out of the exponent before you continue typing. I don't know how many times I've put all of this in the exponent. It's a little embarrassing. I'm going to use my window settings that I had before. So let's set my window. I had -8 to 5, I believe. -100 to, oh no, my scale is 1. Let's not confuse that. -100 to 100. And I put my scale by 10 just because. And if we look at that graph, that's the graph that I had on the previous slide. Now I want to find the local maximum. To find the maximum on a graphing calculator, go to Calc, so second function, trace. I want my maximum, so I'm going to choose option 4. It'll ask for a left bound. Now I'm looking for the maximum, and that's here. So I want to move my cursor so that it's to the left of my arrow. All right, to the left of that maximum point. All right, that's good. I used my arrow keys, hit enter. Again, this is my maximum. I want to use my little spider cursor using the arrow keys. I'm going to move over to the right. And your guess, you don't even have to be a good guesser. But if you want to guess, I'll put it right there. And this is how I got my maximum value at negative 4.3, 73.9. So it'll display it right there for us. Desmos also has this ability. So desmos.com for all your graphing calculator needs. Also on my website, quick search on Tuesday, Johnson UTEP. And I have a free download for a Wabbit emulator. It doesn't work for Apple products. Sorry about that. But Desmos does. But if you have an Android or a PC, you can download the free Wabbit emulator either from my website or you can find it in the Google Play Store. It's the exact same one. All right, let's talk about rational functions. Find the domain, vertical, and horizontal asymptotes for f of x equals 1 minus 5x all over 2x plus 1. All right, so the domain of a rational function consists of all values of x for which the denominator is not 0. So I take this denominator, 2x plus 1. I set it not equal to 0, literally not equal to 0, and I use the same techniques to solve a non-equation that I would an equation. I'm going to subtract 1 from both sides, divide by 2. X cannot be a negative 1/2, which means on our real number line, we pick out the number negative 1/2 and it can be everything else, so interval form. Vertical asymptotes. Vertical asymptotes are found similarly to the domain, but the result is expressed in a different form. So here we say, hey, x can't be a negative 1/2 because it makes our denominator 0. But for vertical asymptotes, we say x equals a negative 1/2 because it's an equation. This is a vertical line that the graph approaches from both sides. As x gets super close to a negative 1/2, there's some craziness going on with our function. In algebra, we learn to find where those places are. In calculus, we look more closely at what's going on there. All right? For now, we just want to know this is where an anomaly is. And once you start studying calculus, you'll be able to describe that anomaly a little bit better. Horizontal asymptotes are found by comparing the degrees of the numerator and denominator in algebra. I see that I have a linear equation in the numerator and a linear equation in the denominator. The numerator is written in ascending order rather than descending order. If we write everything in descending order, this would be a minus 5x plus 1 in the numerator. And that minus 5 coefficient in front of the x and the 2 coefficient in front of the x in the denominator will give us our value for the horizontal asymptote. Remember, it's an equation of a line, so it has to have a y. So it's horizontal. Horizontal lines are always of the form y equals. The leading coefficients tell you what y is equal to. Vertical asymptote, always an equation. Since it's a vertical equation, it's x equals, and it's matched up with the denominator. That's it for other functions. It was exam 2 material for those in my class. Thanks for listening.